Just wanted to start by saying it's a particular delight to speak to physiology and to see you here, David Patterson. I was lucky enough to study physiology under David at Oxford, where instead of worrying about a 70-kilogram male at sea level, I was allowed to indulge in my exams by writing about bar-headed geese and all sorts of other esoteric and far more interesting bits of physiology. So thank you for planting the seeds. The way I'm going to do this is try and quickly tell you what you already know and then tell you why I think we may not know the answers completely. We all know that actually high altitude, it's all about oxygen availability. There's a few other issues there, but we're primarily concerned with oxygen. We know that there's a non-linear fall that's affected by latitude. So Everest happens to be in exactly the right place, that a few gifted individuals, if the barometric pressure is high enough on the day, can get to the top. If it was up where Mount McKinley is in Alaska, the chances are there are probably no humans that could actually summit without supplementary oxygen. Since the barometric pressure is lower in winter, there are very few ascents of Everest in winter. So it's sitting there in the troposphere, so still prone to all the weather effects, which we're increasingly seeing accidents from. Just to put it into context there, the key figure is that at Everest Base Camp, there's about half of the oxygen available as there is at sea level, and by the time you get to the summit, it drops to about a third. Both of those figures are above where humans live permanently. So the longer you spend at altitude, you start suffering from high altitude deterioration. If I was to write a book on summiting Everest, I would call it 1 week in May. And effectively, although you're there for anywhere from 40 to 70 days, you're trying to strike the balance between acclimatizing and deteriorating. And it all comes down to a few days in May, where the monsoon coming in from the Bay of Bengal nudges the jet stream north into Tibet and offers a small window to try and get to the summit. We think that acclimatization follows all the stuff that you already know in order to try and increase the delivery of oxygen. And Lucy's talked about some of those findings from birds such as capillary density. What happens on acute exposure to altitude is it's primarily a respiratory response. So you can see that that's going up straight away and it remains sustained. In response to that, alveolar CO2 drops and stays down. I'm not sure about birds, but certainly in humans, we only worry about the PCO2 at night, where you get into sort of Cheyne-Stokes respiration. During the day when you're active, then physiologically being active means that you can override that desire to have a CO2-driven ventilatory response. Your oxygen saturation drops and stays low. And one of the other features about being at high altitude is even when you give somebody supplemental oxygen, you cannot restore them to sea level performance. Acclimatization does work. What you're seeing here is in green, it's somebody arriving at base camp. And you can see that although they might be in their sleeping bag for 10 or 12 hours, they're spending a relatively short time actually asleep, with quite profound swings in their oxygen saturation. If you look at the red area now, you'll see that once they've acclimatized, they actually get a more restful night's sleep, and their oxygen saturation is far more stable. So traditionally, we think that acclimatization does all of this to increase oxygen delivery, and that's been the traditional teaching in altitude physiology for many years. Because the oxygen delivery is too low, you get a series of illnesses. You've effectively got acute mountain sickness, which is, you can see as a mild form of high altitude cerebral edema, or you can consider high altitude cerebral edema to be sort of end stage AMS. It doesn't really matter. The cardinal feature for acute mountain sickness is having a headache, and then these very non-specific other symptoms, which are often recorded in things like the Lake Louise score. Personally, I don't find that very useful for clinical assessment of anyone who's got an altitude sickness. One of the fascinating things for me is that altitude illnesses occur some hours after you arrive. And I'll just plant that seed and I'll come back to that a bit later. The signs are all very non-specific. Your heart rate's up a bit. Your respiratory rate's up, but it should be anyway. Your urine output's down, but are you spending enough time melting snow? And you may or may not have some peripheral or periorbital edema. I always like to think of the three H's in terms of a differential diagnosis, and I believe that all three of those conditions can overlap and contribute to the pathophysiology of acute mountain sickness. Going into the pathophysiology in a bit more detail, hypoxia is involved, but we don't truly understand why. And I know there's been quite a lot of work going on with that. I'll come back to some of these. We know that your ascent profile does affect your susceptibility to acute mountain sickness. And to date, there are no sea level tests that predict whether somebody can go successfully to high altitude. As an aside and possibly of interest to the sports scientists, I worked with Ben Fogle and Vic Pendleton when they were trying to prepare for their Everest trip last year, I believe now. And interestingly, Ben knew what his resting heart rate and what his maximum heart rate was. Vic knew what her resting heart rate was, but had no idea what her maximum heart rate was, which I found quite surprising. When I asked her, she simply said, I feel a bit more like a Formula One car. Everyone measures what I eat, how I sleep, what my heart rate's doing, and their advice is all condensed down into pedal harder, which I can do by myself. For TV, we stuck them in a chamber and we did their VO2 maxes at sea level and then stuck them in a chamber and made them hypoxic. Ben had a very predictable response. With Vic, it was quite interesting. Her SATs were dropping down into the 50s. The team that normally run the chamber are used to using it to assess people perioperatively, and they were freaking out because we were well outside any of their protocols. And then at the end of it, they said to me, when were you going to stop the test? And I said, when she fell off the bike. And it's a slightly facetious point, but we try and fix on things like, if your oxygen saturation drops below X, then you must be sick. And that sort of reliance on parameters in both physiology and medicine, I think, is one of the blocks that makes us really question what it is that we think we understand. This, again, people know that above sort of 3,000 meters, the advice is that you go up slowly, and your sleeping altitude seems to affect whether you're going to get AMS or not, but widely individual variations. You can use acetazolamide as prophylaxis. It has a number of effects, but primarily one of the things it's doing is increasing that nocturnal respiratory drive. There are hundreds of other things it does, including acting on red cells, which I'm not going to go into today. And here's some evidence of it working. So this is somebody, I don't know if that's, so this is somebody on arrival. Each of those spikes is a breath. Then you get these pauses. It's really annoying. It's hard enough to sleep anyway. When the guy next to you in the tent is chain stoking, you start thinking, okay, it's been 30 seconds. They haven't had a breath yet. I'll go and wake them up. They then take this huge gasping breath. You can see that their oxygen saturation, the red line's just swinging along. My answer to this is I've got music in my ears. So if you're going to die in my tent, you've got to do it really noisily before you'll get me to intervene. Once you're taking acetazolamide, you can see a nice regular respiratory pattern and a much more stable and consistently higher oxygen saturation. HACE, I'm going to skim over it. As I said, it's a sort of terminal, or not terminal, it's the other end of the spectrum with AMS. The symptoms of it are any symptoms of cerebral irritation. The signs, again, you can pretty much have any neurology you like. Ataxia seems to be one of the cardinal features, so we're looking to see whether people can heel toe walk. And we've actually come across, on our trips, we've come across somebody who's I think they're in their 50s, fit climber, had a stroke with no obvious reason for having it. So you can get anything, any sort of pathophysiology you like from cerebral effects. We're not entirely sure what causes it. It does, as I say, involve the white matter. Intracerebral pressure does go up in certain circumstances. More interestingly has been the work looking at venous outflow obstruction and its regulation. And the tight fit hypothesis was simply saying that if you're clever and you've got a big brain and it sits up against your skull, then as your brain expands, your brain's got nowhere to go, so it hurts. If you've got a Homer Simpson brain like mine, it can expand for a long, long time before it meets the cranial vault, and so I'm quite resistant to any form of HACE. HAPE is interesting because, as you know, it's completely different. So it's a combination of hypoxic pulmonary vasoconstriction and leaking endothelium. I actually fear HAPE more than I fear HACE. When I first started going into the mountains, HACE, because of the fact that people can die, used to worry me a lot. Now HAPE worries me much more. Here you can see somebody who's developed this non-cardiogenic pulmonary edema. We're evacuating somebody down the mountain there. The symptoms often preceded by acute mountain sickness, but not always. Nothing specific in there. So yes, respiratory symptoms, bit of a cough, bit of paroxysmal nocturnal dyspnea. The hemoptysis is very subtle. So this is flecks of pink sputum. It's not frank, it's not overt. And unless you are guessing them to cough into the snow or into a handkerchief, if you've got a white handkerchief up there, you're not going to detect this. So again, very, very subtle. And it's only when you see it in the field that you begin to sort of dissect what it really looks like as compared to what the books say it should look like. Signs are also very non-specific. So you've got this blunted HVR, vasoconstriction, increased endothelial leakage. And that's the same patient that's resolved. Okay, so far so good. So that could all be summarised in one of Professor Imre's papers that talks about the pathophysiology of acute mountain sickness. Does everyone believe that?
Of course.
Yeah. Who's had acute mountain sickness here? Okay, just raise your hands. Who got it the night? Who got it as soon as they arrived at altitude? No one. So we've known since at least 1969 that the symptoms of acute mountain sickness don't occur until many hours after arrival. But we still keep saying hypoxia causes acute mountain sickness or altitude illnesses. And what I think we really should be saying is the hypoxia is a trigger for a whole bunch of really complicated stuff that we don't understand that eventually leads to the pathophysiological processes that we recognize as acute mountain sickness. But we miss this because we simplify it too much. Here they were looking at a time lag of between 6 to 96 hours. And I think I'd agree with that. If I've seen someone who gets sick at altitude, it's going to be in the first 1 to 5 days at the same altitude, not if they're not moving up or down. The other thing, if you remember, is that I said that the reason that we have all the acclimatization is to increase oxygen delivery. This is the oxygen content in your blood. And what you can see here is that as we went from London to Everest Base Camp, our oxygen saturation is decreasing. The hemoglobin is increasing, which you would expect. If you look at the oxygen content, it decreased initially, but by the time we arrived at Everest Base Camp, so after a few weeks, it's the same as it is in London. And for those of us who stayed there for a long time, it was higher than it was in London. So if it's about increasing oxygen delivery, why are you getting altitude sickness if there's more oxygen in your blood than there is at sea level? And again, I think this is glossed over and not really sort of spoken about. Sorry, that's just a bit of that's the dissolved amount of oxygen that's ignored. This is Reinhold Messner and Peter Habler, the first people to climb Everest without supplemental oxygen. So they were extensively studied, and people sort of said, well, actually, are they superhuman? Looking at their VO2 max, so this is comparing elite climbers with sort of couch potatoes, no particular difference. It won't surprise you that my VO2 max is nothing to shout home about, mainly because I have to spend a lot of time moving excess weight around that doesn't actually help me move. If we follow that across to the results from our studies, you can see that, so this is looking at the, you can see it yourself, so the partial pressure of oxygen is dropping. The arterial oxygen saturation in this shade here is also dropping, as you would expect. Hemoglobin is going up in the way that sort of we've described, but if you then take the oxygen content up to Camp 3 on the Lhotse face at 7,100 metres, the oxygen content of our blood was absolutely preserved. Yet people are suffering profoundly. Most people are sleeping on oxygen at night, just simply to try and get through the night. And a lot of people can't even reach these altitudes anyway. So again, posing the question, what do we really understand about oxygen in altitude illnesses? Which leads us on to considering the oxygen cascade, and the bit of it that's ignored is the microcirculation of mitochondria. Just to sort of make the point, this is me at Camp 3. I'm playing Scrabble. I've got an oxygen saturation of 56%, so I'm not really good at getting long words out. My heart rate's about the same as it is down here, speaking to you at 108, but I'm perfectly fine. There's some tools available to visualize the microcirculation. I'm quite excited by this. It's almost, to me, like a William Harvey moment of our generation. We can try and look at sort of in vivo blood flow. Here, as you look through this, each red dot is an erythrocyte passing through a capillary. That's the normal microcirculation. If you look at the microcirculation at 6,400 meters, you can see that it's sluggish. You've got some bidirectional flow in areas, and it's compromised. You can see the same thing in sepsis. You can see it in dengue. You can see it in malaria. And you can see it in quite a few pathological conditions. So there's a balance to be struck between the medical and clinical desire to correct people's physiology to parameters we don't understand versus trying to truly have the tools to look at what's happening at the cellular level. This is quite a sad case. This is a lady who tried to hang herself. An air ambulance has arrived. Sorry, I'm just going to walk over here so I can do it. An air ambulance has arrived. She's been cut down from the rope, and what you're measuring here is her tissue oxygen saturation with a device placed on her thenar eminence. It goes crashing down around about 50. She loses any signs of life, so CPR is started. It drops, it then comes back up, and you get the return of spontaneous circulation. It then dips again, and she's given a bit of epinephrine. During this period, she is packaged for flight, which means that she's intubated, put onto positive pressure ventilation, moved into the aircraft. It dips again. There's no response to epinephrine this time. The clinician happens to be a friend of mine, who then, very smart guy, realised this is probably a pneumothorax from the vigorous CPR that she'd had. So puts a needle in to release the air in the chest. It rebounds back up, and then later on during flight, the procedure for this air ambulance is once you've stuck a needle in to release the air, that you make a small hole between the ribs to continue to let the air out under positive pressure. That can get blocked off, so you simply put a glove finger in to release it. The important thing here is that whilst all of this was happening, all the other tools that we use to see what's going on, such as pulse, oxygen saturation, blood pressure, the machine's just cycling through because there's not enough output to actually detect anything. So moving on to what I call the unknown unknowns then. I'm making all this up. I'm just throwing you, hopefully, a few challenges and food for thought. This is a survival curve from intensive care. And we spend a lot of resource and time and effort trying to, as I said, restore people to the numbers that we think work. And what you can see is that actually if we leave people alone, often their own physiology can sort the problem out. Hugh can probably tell you a lot more about this sort of later on, but I think the message is we need to be careful what we're trying to correct and how we intervene. This is, so following on from that, the tissue spectroscopy. I used to be in the military doing a lot of pre-hospital care, and we had a lot of casualties and we had to direct resources. In this study, what people looked at, so the red is the one to ignore. That's your systolic blood pressure. If you were to ask any medical student or doctor, blood pressure is really important. It's not, it's easy to measure. If you look at what's happening with the tissue oxygen saturation in blue, and you look at the heart rate in black, you can see that they're good mirror images of each other. And that's a far better measure of what's actually happening physiologically. They've done other studies assessing people who are having ECMO, extracorporeal membrane oxygenation. And they're trying to look at people who survived versus people who've died. You can see that the quality of imaging has improved. But that's the difference between the survivors and those who don't. So again, we're beginning to get some tools to try and be able to, in this case, it was triaging people, but we're beginning to get some clinical tools that allow us to look beyond beyond the systemic circulation where we're measuring oxygen saturation. I can tell you today that hundreds of people die every day with perfect oxygen saturations in hospitals around the world, because we're not beginning to understand what's going on further down. So I've shown you that already. So of course, we know that hypoxia is much more complicated. Hypoxia-inducible factor, hugely important. I don't understand it completely. I think, to be honest with you, when we started our research with altitude, we didn't know that it existed. Every time I look at it, it seems to be involved with another 10 or 20 interlocking pathways that we need you to sort of dissect out and help us understand. Another way of looking at the pathophysiology of altitude illnesses is to try and combine it all together. This is actually still fairly conventional. I'll leave it up for a second for you to have a quick scan over it. I don't think there's anything in there that you'll find surprising, but I think where we need to start concentrating on is what's happening here in the mitochondria. Whilst I said at the beginning, I absolutely loved physiology at medical school, I hated biochemistry, and I'm having to go back and learn about mitochondria because I just thought about them as being involved in energy in the Krebs cycle, and they're so much more interesting than that. For all the reasons we know, there's all this redox going on here, and Damien has spoken to you about that. From a clinical perspective, we are just beginning to get some tools that allow you to measure mitochondrial function. In this experiment, they progressively hemodiluted a pig, and they measured what was going on in the mitochondria. And what they found is that if they could measure one dilution earlier when they looked at mitochondrial function rather than other parameters. This kit's made by someone at home, but there will be more coming around. And effectively, it's allowing you to measure some redox potential. We have no idea what the correct parameters for these things are, but we're just beginning to get some tools to be able to look at it. This was a team, I think they were in Boston. They were trying to use mitochondrial measurements to predict whether someone's going to have a cardiac arrest. So they've got one paper out, and they said that they could monitor it in real time to see what was happening. I'm just going to end with something that was completely new to me. For altitude illness, every now and then I just cast back to what the Indians are doing. They've got a lot of money in their sort of defense military services trying to find countermeasures for rapid ascent to high altitude so they can carry on fighting up in the Siachen Glacier. So this substance here seems to be quite interesting when they looked at it in rats, where it's reversing some of the effects of altitude, perhaps looking at some of the mechanisms that are more interesting to us at the cellular level. Sorry, I put this the wrong way around. They looked at cobalt initially, but I'm going to go back to the S1P. What you're seeing here, so this is your NC is normoxic control, HC is hypoxic control, And these are various concentrations of S1P that they're giving. And they found that at a dose of 100 mics per kilo, they're attenuating the effect of hypoxia. I think they're going to rapidly move this on to clinical trials if they can. I'm going to stop there. So really, I was just trying to summarize some of the effects of altitude, the pathophysiology that we think we know, how I think there are huge holes in that that involve a much closer meeting of biochemical and physiological minds. I'm not the person to do it. I'm not clever enough. So I'm going to end by showing you my favorite picture. This is climbing to the summit of Everest. This is the shadow of the summit pyramid being cast hundreds of miles over to the horizon. And I'm going to leave you with one of Mallory's lesser known quotes. Says he. Great, thank you very much.